So hello students. So far we looked at the free vibrations. So first lecture was on the free vibration of a spring mass system, and the second lecture was on free vibration of a spring mass damper system. Okay. So we just saw the trends, meaning that the equations and how the solution looks like. So when it start oscillating, then what kind of oscillation can we expect? Okay, and that depends on various factors that we have discussed already. Okay, so today we are going to revisit those systems. However, we are going to get the exact solution by applying the initial conditions, like initial at t equal to 0, what is the displacement x, at t equal to 0, what is velocity. We will apply that in order to get the exact solution. Okay, so there are various ways of doing it. Yeah, so let's start with a spring mass system. Okay, so we start with the spring mass systems, and we will derive the exact solution for that. Okay, so far we got a solution, but we did not apply any initial conditions. So for this equation will be mx double dot plus kx equal to 0. Okay, now we said that solution will be kind of a sine alpha t plus b cos alpha t. Okay, where unknowns are a, b and alpha. There are three unknowns basically, right? Three unknowns. What we are going to do is we have assumed, we are just predicted based on the differential equations that you studied probably last year. This is the solution, expected solution. Okay, that's known by, so this is actually mathematics actually, so that's why differential equation is important for this course. So I assume that you know already. So given this equation, this will be the solution, expected solution of this form. So you put this x in this equation, and we have one equation which has a, alpha, b and everything. So this is equation number one. Okay. Now there are three solutions. We need three equations basically. So one equation is this one. This equation will have a, alpha, b there. Second equation will be the initial conditions, what you call, right? Initial conditions. And here we will say x0. X at t equal to 0 is some value x naught, let us say. At x dot at t equal to 0 is v naught, let's call it like that. So equation number 1, this is equation number 2, this is equation number 3. And you solve this will be a system of linear equations, and from there, from 1 to 3, you are going to find out a, b and alpha. Okay, and this will give you the exact solution. This is what the exact solution will be. Okay, this is one way of doing it. Okay, however, we will use Laplace transform for doing it. Okay, why Laplace transform? Because it's very convenient, it is fast. Basically you can use with even MATLAB, for example, right? Easily available function in MATLAB, so that can do Laplace transform and inverse Laplace transform as well. So it's very fast. Also for control engineering, Laplace transform is used, because it's very convenient because of that. Okay, so we are going to use Laplace transform to find out the exact solution for this problem. Okay. So again, our equation is mx double dot plus kx equal to 0. Okay, and then initial conditions are also given, and those are x at t equal to 0 is x naught, and x dot at t equal to 0 is v naught. So this is what is given to us. We want to solve this one, and this corresponds to what? This corresponds to spring mass system, like this one. Okay, so we are going to solve. Okay, so for this one, x is in this direction, as we have already discussed in last 2 lectures. Okay, now for solving this one, we will Laplace transform of this equation, and then we will take inverse transform and we'll get the expression. So you should be knowing already, but we are going to follow it again and again, and for the whole course actually. So I advise you to actually brush up Laplace transform a bit so that you can follow it, and also since you are going to use it for the whole semester, so you better do it now. Okay, so that way it will be more beneficial. So this equation, we are going to take the Laplace transform of that. So mx double dot plus kx equal to 0. Okay, so that is going to give us m, then Laplace transform of x dot plus k and Laplace transform of x equal to Laplace transform of 0 is 0. Basically, these are the properties of the Laplace transform. That's what I have used it. Okay, where this operator is Laplace transform. Okay. Okay. Now again, I'm going to use the properties of Laplace transform. You may be knowing already. So we have m, the mass, and this one x double dot. If you take Laplace transform of that becomes s square. Okay, and what is s here? Again, should be knowing already. So Laplace transform of a function t, let us say, is equal to 0 to infinity e to power minus st, then ft dt. So this is the definition of Laplace transform. Again, I hope you already know about it. Okay, so it should already be covered in your mathematics course. Okay, so please revise it. Okay, so the property of this Laplace transform is of, if you are taking Laplace transform of x double dot, that is dx d square x over dt square, then this becomes s square, then x s. So this you write it as fs basically. So this fs means Laplace transform of function ft. So here xs, in this case xs is nothing but equal to 0 to infinity e minus st, and then x t dt. This is what the meaning of that. This is same x as here. Okay, so s square, and then s square xs, then you have minus, and then s, and then you have x0, and then minus x dot 0. Okay, x dot 0. So this is the this is from here to here, okay, multiplied by m, okay. Okay, so writing everything this side, okay, then plus k and Laplace transforms Laplace transform of x only, and then you know that this is nothing but equal to x s only, okay, and this is equal to 0, okay. Okay, now next thing is here simplifying it. So we will have s turned this side and all others turned that side. So what we get? We get m s square plus k multiplied by x function of s is equal to, we get s x0 plus x dot 0, okay. This is and multiplied by this is multiplied by m, so multiplied by m like this, yeah, or we get x to power x function of s, capital X, we get s, now x0, x as a we keep it like this only, so s times x at 0 plus x dot 0, okay, multiplied by m divided by m s square plus k. That's what we get, okay. Now let me erase this side. Okay, now given this expression, we can also simplify it further. So m here, we will bring it down. So what we get is x0 s plus x dot 0 divided by, and you have s square plus, and let's call it omega n square here, where omega n is equal to root k over m. Okay, so that we have assumed this earlier also, so we are writing in the same form. Okay, now in order to know xt, we are going to take the inverse Laplace transform of the whole thing of xs, the capital X s is equal to, we are going to take the Laplace transform of the whole thing here. So this becomes x at t equal to 0 multiplied by s x dot at t equal to 0 divided by s square omega n square by this one, okay, and is equal to, what we get is, again inverse transform also has this property, we can take constant out, so this is constant, so L inverse, then we have s over s square omega n square, so this term, okay, plus we have x dot naught, okay, let's divide it by omega n, okay, why? Because this will give a function basically. So omega n here, and then L inverse, then omega n divided by s square plus omega n square. So we get x naught here, x at t equal to 0 here, then inverse Laplace transform, so this divided by this one, then we get this divided by wn, so that we have wn here, and then this term, this one. Okay, now inverse transform of this one, if you see any textbook on Laplace transform, if you see the inverse transform, then the inverse transform of this function s over s square plus omega n square is nothing but cos So we get this one, and value of this one is nothing but cos omega n t. This is known, meaning that if you take the Laplace transform of cos omega n t, you will get s over s square plus omega n square. So hence the inverse of this, you get cos omega n t. Okay, and plus you get x dot 0, okay, divided by omega n, and inverse of this you get, if it is cos here, it will be sine here. So this is sine omega n t. Okay, so this you get the exact solution. Okay, so xt becomes x at t equal to 0, which is equal to x naught, you can put it here, then cos omega n t plus x dot at t equal to 0, which is equal to v naught, so you can put v naught here, and then divided by omega n multiplied by sine omega n t. So this is the exact solution that we were looking for. And similarly, we can solve the damped problem as well. Okay, so our equation for a damped problem, so what we mean is we have a spring here, a stiffness K, then we have damping coefficient of the damper C, and then this mass here, which is, let's say, oscillating. This is the deflection or displacement. Okay, and it will have velocity this in this direction positive, and so on. So for this one, we know that the equation for this is mx double dot plus cx dot plus kx equal to 0. And we simplified this further, and we represented this as x dot, then 2, then we call it zeta, then omega n x dot plus omega n square x equal to 0. We wrote it like that yesterday. So where zeta we call is equal to c over 2 root km, and omega n was equal to root k over m. So this equation we have used. Okay. Now we had 3 conditions. In one condition we called it critically damped. Right? So we will start from that. The critically damped, and when zeta equal to 1. Okay, so we call it like this. Yeah. Okay, so for critically damped conditions, what we get? We put zeta equal to 1 here, and you will get for that your equation becomes x double dot plus 2 omega n x dot plus omega n square x equal to 0. So this is the equation for critically damped system. Okay. Now, if given this equation, we can again solve a different way. So one way will be to first guess what kind of solution it will be. Okay. For that, since we know that here zeta equal to 1, and here discriminant. Okay, so discriminant, that's b square minus 4ac, right? So in this case, what we get is 2 omega n square. Okay, this is 2. So 2 omega n square minus 4 times 1 omega n square. What we get is equal to 0, right? So since this is discriminant is 0, okay, that means it has repeated root. Yeah. So because of that, this will have, instead of assuming solution will be something like x t equal to a e alpha t, or a1 a e alpha t plus b e to power alpha t, this kind of thing will fail here, because there is no 2 alpha 1 and alpha 2. Here alpha 1 is equal to alpha 2, basically because of this discriminant being equal to 0. Yeah. So in that case there is, the solution will not be a times e to the power alpha t, rather in such cases xt is proposed as xt equal to a plus b times t and then e to power alpha t. So this is the right, if the discriminant is equal to 0, then solution will be of this form of a plus bt times e to power alpha t, and this you have to put here in order to solve it. And then again, if you are going to put this value here, then you have how many variables? We have a, b and alpha like earlier. So 3 equations you need. So if you put this value here, already you have one equation involving a, b and alpha, and then other 2 will be initial conditions. Okay, so initial conditions. Okay, and like earlier, here also we are going to use the same thing, meaning that x at t equal to 0 is x naught, and x dot at t equal to 0 is v naught. So we have equation number 1 with this put here, equation number 2 and 3 is a total 3 equations. We get 3 equations involving a, b and alpha. Hence you solve them, you find out what is a, what is b, what is alpha, you get the answer. However, you have to be careful. Yesterday we did not put like this. We assumed, since we were solving for all together, all the 3 cases together, for damped, under damped, critically damped, we assumed the solution was of the form of a times e to power alpha 1t plus b e to power alpha 2t, means alpha and alpha 1, alpha 2 separate. So we assumed of this form, we did not assume this form. Hence the answer that we got for this one, for critically damped, was not of this form, because our assumption was not correct. Okay. However, if you do the Laplace transform method, you will automatically get the right solution, and that's the advantage of the Laplace transform method, and hence we are going to use it again and again. So let's apply the Laplace transform method for solving this differential equation, where this is same as this one, but zeta is equal to 1, because this is critically damped condition. So let's start from the equation. So our equation x double dot plus 2 omega n x dot plus omega n square x equal to 0. So this is the equation. Yeah. Okay. And initial conditions given, that x0 equal to x naught given, x dot 0 equal to v naught given. So they have to be given. Yeah, because this is second order differential equation, hence there will be 2 initial conditions required to exactly find out the solution. Okay. So given this, now we are going to take the Laplace transform. We will do the same process again and again. That way also you will have repetition basically. So omega n x dot plus omega n square x equal to 0, or we are going to do the same thing that we did earlier. So here we have L of x double dot plus 2 omega n, okay, and then we have of x dot plus here omega n square and equal to 0, or if you take Laplace transform of this one x double dot, that is equal to, as we have written earlier, so this value will be equal to s square, then xs minus x0 s minus x dot 0. So this is one thing, okay. This we get for this one, so we write like this. Okay, so let's divide it like this one. We will use this space as well. So we have this one plus, then you have 2 omega n, and then Laplace transform of this one, this value is equal to s x s minus x0. Again, all these things are standard actually. So if you want to quickly look at it, you can also go to Wikipedia. Okay, just search for Laplace transform, go to Wikipedia, you will have a table which will give you these properties. Okay, so this is easy to get. Okay, s x s minus x naught plus omega n square, and then we have x s and equal to 0. Okay, or now all the coefficient of capital XS will keep this side, left side, the other side, all others will go. So here we collect XS is common, and then we have S square. Okay, from here we have plus 2 omega n s. From here we have omega n square. Okay, so we get this one is equal to the other side. We have this negative, 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 all negative basically. So what you get is x at t equal to 0 multiplied by s plus x dot 0 plus x at 0. Okay, so all plus signs, so this and this. Okay, so this will not, nothing has, this and this has no coefficient, but this one has 2 omega n, so we will multiply it by 2 omega n, 2 omega n. Okay, so it's like this. Okay. Now we can simplify further, so xs will be written as, so we have this term, so we write x at 0 multiplied by s plus x dot 0 plus x at 0 multiplied by 2 omega n and divided by s square. If you look at it, this is s square plus 2 omega n s plus omega n square, so we can also write it as s plus omega n whole square. We can also write like that. Yeah, so okay, so once we have like this one, here we can simplify this further. So we have xs equal to, now we can have s here, or we take omega one of there are two of them, two here, so we take one of these here, so we will have something like this, x naught, I'm just writing like this, so we have x naught multiplied by s plus omega n. Okay, so x naught s, we get the first term, this one, and then x naught omega n, so this is with s, this is with omega n, so we get this term. Okay, plus x dot 0 plus x naught omega n. So see here, so it has 2 omega n x naught, so 1 omega n x naught is here and the other we write here. Okay, so split into 2. Why? You will see later. Okay, so we are going to get into a standard form something whose inverse Laplace transform is known, so that we can get the function. That's the idea. So that's why we are rearranging it like that. So this and multiplied by all of it multiplied by s plus omega n square. Okay, and then so this will be simply x s is equal to, we get x at t equal to 0 multiplied by, now s plus omega n is here, divided by s plus omega n square. So what we get? We will simply get the first term will be simply x naught x0 divided by s plus omega n. 1 s plus omega n will be cancelled from here. So we get x0 divided by s omega n square, and plus the second term we get is x dot 0 plus x0 multiplied by omega n. Yeah, okay, and let's divide it by omega n. Why? Because we need it. Multiplied by omega n plus s plus omega n square, like that. Okay, so further simplification will be like this one. Why we wrote like this? This one omega n over s plus like omega n. This way we may get a simple form. Okay, we will get a standard form, a standard expression whose inverse transform we can easily do. Sorry, actually we don't need the don't need to divide by omega n and multiply here. So this is fine. Okay, so we have multiply here, so divided by 1 over s plus omega n square itself. If we invert, we will get a function. Okay, so now if we want xt, so then we take inverse transform of x s here. Okay, okay, now if we take inverse transform of this one of 1 over s plus omega n, which is equal to, this will be value equal to x at t equal to 0 and e minus omega n t. So inverse transform of this one will give us x naught e to the power minus omega n t. Now inverse transform of this term after plus whatever we get, that term will give us plus and then this divided by this one, or this multiplied by this. So this one is a coefficient which is a constant, so we get simply x dot 0 plus x naught omega n. Okay, and then we have this term. So inverse inverse Laplace transform of this 1 over s plus omega n square term. Okay, so if 1 over s plus omega n, it is e to the power minus omega n t. 1 over s plus omega n square, we get t times e to power minus omega n t. So this is the solution. This is the exact solution. So for this one was for critically damped condition, right? System. So for this, the exact solution is xt equal to x at t equal to 0, which we said x naught times e to the power minus omega n t plus x dot at equal to 0, which is v naught, plus x0, that is x naught, times omega n multiplied by t multiplied by e to the power minus omega n t. So we automatically get a t term there. Okay, and as I said earlier, there are other ways of solving this one, but there you have to have the usual method where you have a guess. So in your guess itself, the t has to be there, and that guess actually comes from the well-known theories, basically. So which are already something which is already well known. So this is this form is the solution. From there we find out the coefficients. Okay, but in this case we don't have to assume anything, any form of solution. We just apply Laplace transform and then inverse it, and we get the function, and it automatically has the initial conditions applied. That's the beauty of the Laplace transform. Now let's look at the overdamped condition. We will apply the same methods that we have been applying. So overdamped now, overdamped condition. Okay, so the equations remains the same, x dot double dot plus 2 zeta omega n x dot plus omega n square x equal to 0. And what we know here is zeta is greater than 1, is greater than 1, because this is overdamped condition. Okay, so that really means that I will come back to that what I was going to say. Okay, so again, if you wanted to solve it, how will you solve? In this case, we will assume solution which will be x equal to a to the power e alpha t, and you will put this to there and solve for alpha. You will get 2 alpha. Alpha you will get alpha 1 and alpha 2. Okay, and hence the solution will be of the form equal to x equal to a1 e alpha 1 t plus a2 e alpha 2 t. Okay, the solution will be something like this one. Okay, so since alpha 1 and alpha 2 is known together, okay, so one equation itself gives alpha 1 and alpha 2. So both are known together, so that equation required for that, and then there are 2 more coefficient a1 and a2 to find out. Okay, so basically you have 3 unknowns. So you have a1, a2, and you have alpha 1, 2. So alpha 1, 2 again is known together because this becomes a quadratic equation, and quadratic equation you solve only one equation. Quadratic equation is only one equation, but it gives 2 values for the same alpha. So actually for this, finding out alpha 1, alpha 2, you have only one equation needed. So one equation for this, one equation for this, one for this. So total 3 equations needed, and you have one equation. So this is the one which will go here. So you have one equation from here. Second equation you get equal to x naught, and third equation equal to v naught, and hence this is 1, this is 2, and there are 3 equations will give you the exact solution. You can find out the exact solution. Okay, again we are not going to proceed this way. Okay, so we have done that already yesterday, although we did not find out the coefficient, but we had the form, the C1, C2 or the coefficient we did not find out based on the initial condition. However, we had the solution which was correct basically. Yeah. So applying this automatically will give you the correct solution. So this is one method. But again, for this course, we are going to apply Laplace transform method again and again. Okay. And you will see why it is very important. In control theory, we will rely on Laplace transform only. Okay, so it has even the greater role to play, basically not only for finding the solution, but it's also in different way, basically. That way you will understand when you are doing the control theory. Okay. So basically this we are going to solve using Laplace transform. Okay, so we have this problem to solve. X double dot plus 2 zeta, where zeta is more than 1, omega n x dot plus omega n square x equal to 0, and like earlier we are going to take the Laplace transform of that. So we get x double dot plus 2 zeta omega n x dot plus omega n square x, and is equal to 0. And we will do the similar things what we did for previous two cases. So what we get? We get from here, we get s square xs plus minus s x0 minus x dot 0. Okay, so let's have this here. Okay, so this is for the first one, then the second one plus 2 zeta omega n, and then we have s xs minus x0. Okay, so this is for the second one plus omega n square xs is equal to 0. So we have that. Or again we do the same thing. We have to find out what is the coefficient of xs, and that we are going to have in common, and then we have s square. Then from here we have 2 zeta omega ns, and then we have omega n square. This is equal to, from here we get s x0 plus x dot 0, and from here plus 2 zeta omega n x0. Okay, 2 zeta omega n x0, we have like this one, and hence we find xs equal to s x0 so right x0s. Okay, also here, okay, let's write whatever we get here. So x dot 0 plus 2 zeta omega n x0, and divided by, we have s square plus 2 zeta omega ns plus omega n square. Okay, so now we have to take inverse Laplace transform of this function, and we will get the actual solution. Okay, so now before we do that, we have to simplify it so that we can readily recognize, and we can take inverse Laplace transform or get the actual function. So right now in this way it is difficult to actually which all functions will appear here. So we are going to simplify this one first. Okay, so if you look at this will be, let's write this one is x0s plus x dot 0 plus 2 zeta omega n x0, divided by, and here we can write it as s plus, since this is 2, so we can write zeta omega n. So zeta omega n whole square. So then we will get s square, then we get 2 zeta omega n s plus zeta square omega n square. So we get zeta square omega n square extra, right? So we have to subtract that here. So we get zeta square omega n square plus omega n square, like that. Okay. Now we know that zeta is more than 1. Yeah. So that really means what? That means we have to write like this, is equal to, again, see here, s plus zeta omega n. So we have to write, if s is there, so that we have similar thing there. Whenever s term is there, we have to bring this the same format. Somehow we have to get s plus zeta omega n. That way we will get some function, intrinsic function, inverse of that. Okay, so that's what we will do here. So we have x0, and then we borrow one of these from here. There are 2 of them, so we get 1 from here. So this is s, and then x0, and then 2 zeta omega n. So we get 1 zeta omega n from here. Okay, so plus we have x dot 0 plus zeta omega n x0. So we have that, and divided by we have s plus zeta omega n square, and we have minus omega n square, and we have zeta square minus 1. Okay. Since zeta is more than 1, this will be a positive number. Yeah. So omega n square multiplied with zeta square minus 1 will be a positive number, the whole thing. So this is positive, a positive here, a square minus a positive number. Okay, so that means we can also write it like this. So that will be equal to x naught times s plus zeta omega n divided by x dot 0 plus zeta omega n x0 divided by s plus zeta omega n square. Here we can write as there will be 2 terms basically. So there will be 2 terms. So there will be this plus we have omega n root j is minus 1. So this will be one term, and multiplied by we have s plus zeta omega n minus omega n root zeta square minus 1, like this. Okay, the plus and minus, so plus minus, this becomes a plus b multiplied by a minus b, you get a square minus b square, same kind of thing you get. So this is a square, this is minus b square, so plus a minus plus b minus b here. Okay. So we got this form now. We have to simplify it further, and how are you going to do? Now see here, if s plus zeta omega n here, s plus zeta omega n here plus, here minus, if we add them together, this and this, we get 2 times of this one. Yeah. So what is the meaning? The meaning is we can write the first term as x0, then you have 2 of them, so we write divided by 2, and now we can write, separate it out. So we can write 1, this one, we can write 1 1 divided by s plus zeta omega n plus omega n root zeta square minus 1 plus 1 divided by s plus zeta omega n minus this one omega n root zeta square minus 1. So this till here we have done. From here to here we are done like this one, plus, okay, so plus thing I am going to write here, okay, so plus this we are going to write it here. Okay, so plus, okay. So basically this dot 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 means this, plus we get this term here, so we get x dot 0 plus zeta omega n x0, x dot 0 plus zeta omega n x0, okay, and then this term divided by this multiplied by this. So now if we subtract this from this, so s plus zeta omega n, and here also s plus zeta omega n, so this will cancel out. Here omega n times zeta square minus 1, and here minus, so minus plus, so this minus this will give you 2 times omega n multiplied by zeta square minus 1, okay. So let's write this one like this, okay, and we divide it by 2, divide by 2 times omega n root zeta square minus 1, and then we have multiplied by, and we have now this term minus this term here. So this will be 1 s plus zeta omega n plus omega n zeta square minus 1, and you have minus 1 over s plus zeta omega n, sorry, here should be minus, okay, this will come first, this will be plus, will come here, so omega n root zeta square minus 1, okay. So basically the whole thing, this expression will be equal to this divided by this multiplied by this, and will equal to this term plus this term till here, it comes till here, okay. So that means now this is of a form that we can readily recognize now, okay, and we can actually find out the solution basically, yeah. So f or xt is equal to inverse Laplace of xs, okay, and hence we get xt equal to, first we take the inverse transform of this part plus inverse transform of this part will be the solution. So xt will be x0 divided by 2, okay, inverse transform of this s plus some value, some constant here, from here to here, 1 over s plus alpha, inverse transform of that is e to power minus alpha t. So we get here e to the power minus, we get minus both of them, minus zeta omega n plus omega n root zeta square minus 1 times t. So we get inverse transform of that, we get this value. Inverse transform of this one, we will get plus e to the power minus, same as similar process here, so we get zeta omega n, okay, and here we have minus here in this case now, okay, so minus and omega n root zeta square minus 1, and then we have t. Okay, so this is done. Now this part, okay, so this is done, plus we have to have this one now, okay, so we multiply this one, so we have x dot 0 plus zeta omega n x 0 divided by 2 omega n root zeta square minus 1 and multiplied by, okay, and then we will have inverse transform of this one, so 1 over s plus here zeta omega n minus omega n, so this term and this term are same, so value will be same as this one, so this will be e minus zeta, so let me simplify so that it will also save some space, so minus we will take this omega n outside, so omega n, then zeta, so omega n outside, so zeta minus zeta square minus 1 t, okay, okay, and then we have this this term, okay, this is similar to this term, okay, so you can see the expression will be plus e to the power minus omega n, we have taken, so the expression will be similar to this one, so omega n, then zeta plus root plus zeta square minus 1 and then t, okay, like this. Okay, so the solution is, this is the whole thing is solution. This is from starting from here, okay, till here is the solution. Okay, this is a big solution. We can simplify it further because what you see is this term and this term is same, and similarly this term and this term is same, so you can combine them together or you can simplify it, yeah, but this is the basic idea how you find out the exact solution. In this solution, everything, all coefficients are known. You have x at t equal to 0, we call it x naught, then x dot at t equal to 0, which we call the v naught, so that is there. So all other things are, everything is known here, so you get solution in closed form.